All right, so let's continue on with this confidence interval for a population mean where we have a large sample or the population standard deviation is known. Now, I demonstrated this and showed that our confidence interval for mu could be written as x bar minus margin of error, x bar plus the margin of error. Now, there are other ways that this can be written. Another common way, not the one that I recommend for you to use in this, is you could say confidence interval, and then you could say x bar minus margin of error less than or equal to, well, actually let's make it less than, mu less than x bar plus e. So you could create an interval that way. I just want you to be aware that that could be shown or written like that. I do not suggest doing it like that. Do it like this, and remember we have to state what that confidence level is. So a 95% confidence interval for mu, or a 90% confidence interval for mu. Now, I want to continue with this, that if you remember looking at some other examples, that our margin of error doesn't always come out pretty. The margin of error could be 2.17, 6.18, 3.94, right? It doesn't always come out pretty. But when you hear of confidence intervals, usually you hear things given as like plus or minus 3, give or take 2, right? You don't hear people say plus or minus 3.19. They just don't do that. Well, how do we do that then? It's like we want to have a certain margin of error instead of just coming up with randomly. How can we find that out? And how we do that is we kind of reverse the process. If we look at our margin of error is equal to z sub c sigma over the square root of n. Well, sigma, the population standard deviation, is what it is. There's nothing we can do about that. Z sub c is dependent on our confidence level. So that's stuck being whatever it is depending on what confidence level we're looking for. If we want to set a specific margin of error, the only way we can change that is by changing the sample size. So what I want to look at right now is how do you determine what sample size is necessary to get the required margin of error? And yes, you could just take a really large sample to make sure that you get the margin of error you're looking for, but then you may be doing a lot more work than you need to. You may be taking a sample of 20,000 and you only needed 1,200 to get the margin of error you're looking for. So what I'm going to do here is I'm going to take this equation, E is equal to Z sub C sigma over the square root of n, and I'm going to solve for n. So first thing I'm going to do is divide both sides by Z sub C, and no, you don't have to be able to do this algebraic manipulation yourself. We will come out with a final formula, and you'll be able to use that formula. So E divided by Z sub C is equal to sigma over the square root of n. Well, I want to get n by itself. Being in the denominator when you're trying to get something by itself is never a good thing, so let's multiply both sides by the square root of n. So I have the square root of n times E over Z sub C is equal to sigma. I'm trying to get n by itself, so I'm going to divide both sides by E over Z sub C. When you divide by a fraction, you multiply by its reciprocal. So the square root of n is equal to sigma times Z sub C over E. Now I'm going to rewrite this just a little bit and say the square root of n is equal to Z sub C sigma over E. And then if I want to get n, I need to square both sides. The square of the square root of n gives you n. Remember, x is equal to the square root of x squared. Same thing here. So if I square the square root of n, that's going to give me to n. I do the same thing on the other side, and I end up with n is equal to z sub c sigma over e squared. And what this will give us is the minimum sample size necessary for us to get that margin of error at the associated confidence level. Now, again, sigma has to be given to us, or if it's not given to us, then we need to find a sample standard deviation. But you're like, wait a second, we don't know what our sample size is. So what can we do if we don't have sigma? We can take a large sample, anything greater than 30, and find a standard deviation from that and substitute it in. So now that we have all that, that's going to be our formula. I'm going to move that up here. N is equal to z sub c sigma over e, the quantity squared. We're going to reverse the process. Okay, so I have been tasked with finding a 95% confidence interval for the population mean with a margin of error of 2 when the standard deviation, the population standard deviation, is known to be 0.7. What size sample do I need to create this 95% confidence interval? Remember, the purpose of this is we want to do, I hate to word it like this, but we want to do as little work as possible. Because if we're doing this research, it costs money for everything, every single member of our sample. We have all the things that we have to send out or all the work that has to be done. So the more we have to do, the larger the sample, the more time, energy, and money that's going to go into this. And we don't want to spend any more than we have to or exert ourselves any more than we have to. So we want to minimize our sample size. We want the bare minimum that will allow us to meet these criteria: a 95% confidence interval or confidence level, and a margin of error of 2, given that our population standard deviation is 0.7. So we're going to use this formula. There you go. Well, first, 95% confidence level. We look at our little table, 0.95 gives us 1.96. So z sub c is equal to 1.96. So that's a good start. So now we're going to plug it in. N is equal to z sub c, 1.96 times sigma 0.7, 0.7, over our margin of error, 2, and all of that squared. Okay, so now that we've got that, let's do this calculation, and this is going to come out really strange. Actually, let me do a modification, and we'll make this standard deviation 30.7. Okay, I just put a number there that was not going to work well. So we know that the population standard deviation is 30.7. So if you've been writing these down and doing the calculation along the way, realize that sigma just changed to 30.7. Why? Because I have the power to change that number. You would not in the real world, but if you were to run this with the 0.7, you'd see why I did. Okay, so now we're just gonna plug this in and see what happens. So 1.96. So I got an extra 6 on that, 1.96 times 30.7 divided by 2, and then square that, and I get 905.167396. Okay, so we multiplied 1.96 times 30.7, we divided that result by 2, which gave us just under 30.7. In fact, it gave us 30.086, and then we squared it and we got 905.167396. Okay, so now that we have that, the question was, what size sample do we need to meet these criteria? Well, we need 905.167396, but obviously we cannot have part of an item in our sample. Our sample size has to be a whole number. So it's either going to be 905 or 906, depending on how we round it. When we are finding the sample size, the minimum sample size necessary, we will always round up. So this 905.167396 is going to turn into 906. So our minimum sample size would be 906. Why did I round up? Because we need a minimum of 905.167396 to meet our criteria. If we rounded down, we would not have that minimum, we would have less than that value. Right? We need at least this many, so we need at least 905 and a little bit. If we get rid of that and a little bit, we haven't reached that at least. We have less than. So we have to round up. If this came out to be exactly 905, then fine, we need 905. But if it's at all above that, even 0.000000001, then we're required to round up. Never round down when finding the sample size. But that's our process. So we just reversed this formula to solve for n, and we just get our critical value just like we did before off the table, our margin of error, our standard deviation, and we plug it into this reversed formula, and then round up. And that's how we find the minimum sample size necessary.